everybody. Thanks so much for joining us today. I think you are going to love this presentation and this project. Super exciting. Skylar and Scott are going to be talking about what I think is incredibly inspiring because it's not only a single family PHIUS passive house project, but it's been around for a year. And it's actually generating more electricity than it's using, even though that first year was way hotter than typical and also way colder than typical in the winter. We have two presenters. Skylar Swinford is the principal of Energy Systems Consultants, which is an Idaho-based building energy and enclosure consulting firm. He's a certified passive house consultant, a PHIUS rater, and a BPI building analyst and envelope professional. Skylar's consulted on hundreds of residential and commercial building projects in the Northwest and across North America, and he lives in this house, and it is beautiful. Just wait till you see pictures. Scott, oh, I'm gonna mess this up. Yribar, I think I got it right. Yes, okay. Is an architect with a passion for how to fit things together. And whether it's the facade composition or a window installation detail, he's really interested in how different parts can be assembled to make a whole that's both functionally optimal and beautiful. Scott is committed to finding solutions to the tension between architecture and energy efficiency. And like Skylar, he's a PHIUS certified passive house consultant, and he's also completed several projects that have been certified to passive house standard. Take it away, guys.
Hey, Bev, thanks for the intro. Scott's going to start off sharing his screen, and then we're going to transition midway.
So yeah, it's been a pretty cool project to be a part of. I'm going to kind of run through some background information just to give everyone an idea of the project. And then we'll turn it over to Skylar, and he'll talk a little bit more about some of the monitoring data that he's been able to collect over the past year. So we had a great project team. Skylar, like Bev said, is the owner. We've had input from all kinds of different people, but we've been able to work with Skylar on a couple of different projects, and this one was a lot of fun, and we learned a lot. Got to work on some cool details. So here's just a few numbers for everybody. The project is located in Boise, Idaho, so climate zone 5B. It's certified to the PHIUS Plus 2018 and the Source Zero standard. You can see some of the passive house metric numbers there. Won't go into those too much, but everything met the standard. And it was completed in 2021. So this is the situation. The project is an infill lot, so kind of hard to come by, but there was a small lot 30 feet wide in Boise's historic north end. So it was oriented basically the long axis east-west. So this, along with the design review, the historic design review, really kind of shaped the size and the volume of the project. Just run through quickly some plans. It's a 3-story house. There's a basement with 2 bedrooms, bathroom, mechanical laundry. The main level is basically a living, dining, kitchen, the entry and small half bath. And then upstairs, there's a primary bedroom, primary bath, and basically kind of a primary suite upstairs. There's also a garage that's not shown here, up on the west side. So here are just a few images from the interior of the project: the kitchen, kind of kitchen dining area, the staircase. This is a view of the staircase from up above, looking down, kind of goes all the way down through 3 levels. This is sort of the volume of the space under the roof, which we were limited on height. So this is kind of how that happened. Looking through some of the circulation space on that upper level. So the site, as I said, it was really narrow, 30 feet wide. So excavation was challenging. You had to go pretty much right to the property lines. Just a few snapshots of the construction process, not getting too much detail, but this is Skylar's heated dome for his ICF foundation. So this is when they're forming that. Getting ready for to prep the subslab. You can see the ICF walls are completed, pretty much completed there. So the project is a double stud wall. You can see the sort of that double stud wall taking place on the first level. Here's a shot of the basement window. The steel window wells were just put in there. So like I said, the living space on the upper level is under that roof. So it was kind of stick framed with 9.5-inch rafters. The air barrier was the exterior structural sheathing. So they used a zip system, and all the joints were sealed with fast flash. That was the primary air barrier, or the air barrier. Windows were aluminum windows by Glow Windows. And then the orientation of the project, basically there was almost no south facing glass. Everything was either on the east facade or the west facade. So to help control some of that, those solar gains, we used these motorized Venetian blinds that on the exterior of the window, and then they retract into a pocket on the facade so you can't see them. Those were also provided, they came with the windows from Europe. The heating and cooling system is a single 1-ton system. This is the outdoor unit. Inside, there's a single air handler. The project is broken up into 3 zones, 3 mechanical zones, so basically by floor. So in order to use that single air handler unit, this air zone system was used. So it's a motorized dampers, it's a smart controlled dampers. So the one air handler was broken into 3 zones by floor, thermostat on each level, and that communicates back to the control board and can control the air handler. So this was a really cool way to be able to use basically the appropriate size piece of equipment. So small, but not have to get several units. Ventilation was a Zender Q350. Skylar will talk about it a little bit more, but there was an additional filter housing. You can see sort of above one of those manifolds. That's why they're oriented kind of in a different way. You don't see there's a filter housing that actually is working very well when we've got some of the poor air quality events when there's forest fires in the area. Domestic hot water is provided by the Sandin or Sanco heat pump system. You can see the outdoor unit on the facade, and then the indoor tank is in the basement. There's also a hot water recirculation system, and Skylar can talk more about this, but he started with the smart plug. So sort of it's supposed to learn the hot water, the behavior of when you need hot water. Guess that didn't work out really well. So they went basically to these on-demand wireless on-demand switches. So that's kind of an important part of that hot water
Scott,
system.
I'll interject real quick. Yeah, basically I switched to these battery operated wireless little switches that are like 1.5 inches by 1.5 inches. They're really small and slim, and we're able to put one of those at each hot water fixture. And it uses the Zigbee protocol, and it's been rock solid. There's never been any issues like with firmware updates breaking the connection. It's really easy to program the time you want the switch to run. And so basically when we push that switch, depending on where the fixture is located, it's like a 2 to 3 minute recirculation time. And it operates, 3 to 4 times a day typically. So it really cuts down on how much it was running on that smart plug. It was running it basically was going into like pulse mode, where it would run incrementally based on the temperature sensor, and it would kind of result in hours a day of recirculation. And so that using the on-demand switch was really beneficial, and not having to hardwire something was really nice. Basically, the switch activates the plug and the pump turns on, and then for the timed amount, and then it turns back off. And then I will say, living in the house, what's really amazing is how instant the hot water is, because we took the recirculation trunk line and brought it almost entirely up to the fixture. So there was just the smallest branch coming off of it, if any, at times. And so it went right to the valve, and the water is literally hot in just like a matter of 1 or 2 seconds, if that, once the recirc line is primed. So I really recommend trying to get your recirc loop as close to the fixture as you possibly can.
Okay, and the last thing here is the PV system. So there's about an 8 kilowatt PV system. The orientation of the project being east-west wasn't great for having south-facing windows, but it worked out really well for the PV panels. So if you have any questions about any of those specifics, we can come back during the question and answer. But wanted to turn it over now to Skylar, and he can kind of get into some really interesting data that he's been collecting.
I just want to give a little more context. I saw in the chat there were some questions about where the project was located, and it is in Boise, Idaho, which is in climate zone 5B, and we have all 4 seasons here: winter, spring, summer, and fall. So it's good. We'll be able to look at the monitor data for the project and look at some kind of extreme summer weather and winter weather, and how the building performed. There's about 5,000 heating degree days. We're a little around 2,800 feet of elevation, about 1,000 cooling degree days. In terms of extreme temperatures, the ASHRAE handbook climate data, this is the 2021 data, which I recommend using the most recent data from first your dry bulb temperatures for sizing your equipment from the latest ASHRAE files, because it does change and evolve. I've seen projects using like data from 2009, which has a substantially different design temperature. And when you're designing a heat pump, in my opinion, you want to be as aggressive as possible when you size it and use the correct design temperatures, and don't be overly conservative and add padding to your calculation. But just to give you an idea of over a 50-year period, you can get this extreme dry bulb minimum temperature in our region of about -11 degrees Fahrenheit, and then as high as 111. And we have some monitored data when the outdoor temperatures were about 106 and 0 degrees. So we came pretty close to some of these extreme temperatures that we'd expect over a 50-year period during the monitored period of the project. And then in terms of looking at the monitor versus modeled performance, it's really important if you're trying to get an accurate assessment of your heat pump usage, for example, which is really dependent on the climate. I really recommend normalizing the weather data. When you take the climate data in your PHP or WUFI, it's often different than the actual measured data for that year because there's year-to-year climate variability. In our case, the PHIUS climate data set used in the WUFI passive, our winter was about 15% higher than that climate data set in terms of heating degree days. So it was 15% more severe. So you'd expect about 15% more energy usage. And then you can just see from the ASHRAE climate data, this really does kind of show the warming trend of less heating degree days for winter as ASHRAE updates their climate data. And then on the cooling side, we had a fairly extreme summer. And so we had about 50% more cooling degree days than typical design year would have had. And so that's going to be reflected in the energy usage of the project. Kind of zooming out a little further, I'm going to be talking about the energy use intensity of this project. And that's basically the amount of site energy used on the project per square foot. When you take all the BTUs that the project used for heating, cooling, lighting, et cetera, and you take all that site energy and turn it into BTUs and divide it by the square footage, this is kind of, this is what the EUI is. And when I'm modeling a project, I really like to have a good baseline EUI of the existing building stock. So I don't create a hypothetical baseline model for the project that isn't grounded in reality. And so it's really good to have some monitored data. In our region, we have data from NEA where they go in and they sample the energy use of actual homes across a range of years, and they provide that data. And you'd expect kind of an existing home in our climate zone 5 region to have an EUI in the 40 range. And compared to that, Pacific Northwest National Laboratory, PNNL, they publish a study when there's for every new code cycle. And for climate zone 5, which is here in the middle, for a 2018 project, they'd expect an EUI of about 45. And if you follow 2018 IECC, and then 41 if you follow 2021 IECC. And nationally, you'd expect kind of a new build building to be in like the 30 to 35 EUI range. If you kind of average it out nationally, that's just to give you some context. And I've talked about some of these EUI numbers. Keep in mind, if you were doing an all-electric house with a heat pump, the EUI would generally be lower than these advertised EUIs because this assumes a mixture based on actual kind of construction of like percentage of heat pump adoption versus gas furnace adoption and electric resistance adoption. So it's kind of not an apples to apples comparison, but what I can do, and which I did on the left, is I basically took our project and modeled it in WUFI passive. with the same lighting load, same appliance load, same hot water usage, same occupancy loads. And that's the value on the far left. And basically, I just took our certified model that we submitted to PHIUS with all the final data for the project and changed the building enclosure. And that estimates that our project, if we just built to code minimum levels of air leakage, didn't use heat recovery ventilation, and had kind of code level roof and wall and floor assemblies, we'd expect an EUI of about 36. And in the middle, our measured EUI is about 15. And then on the far right, you can see the modeled EUI was predicted to be about 13. And so the measured and modeled were quite close. Really, the biggest discrepancy in modeled versus actual performance on my project is the hot water. And we can kind of discuss that in the Q&A section a little bit more. I've got some more information on it. But what I want to address is that the biggest knob that we have to turn, at least in projects in climate zone 5 that have a lot of space conditioning, is the thermal loads. Like 50 to 80% of the loads of a building are thermal loads. Most of them space heating, and then some space cooling, and then domestic hot water. And so when we're looking at how we impact the energy use of the building, it's really less so about appliances and lighting. There's incremental gains we can make there, but it really comes down to the thermal enclosure. And I think that's oftentimes missed. And then just to give a little more context, if we take the actual temperature climate data and we change the set points to what we use in our home, we don't use the 68-degree set point, at least not typically in our house. And we don't use the 77-degree cooling set point. We like our home to be a little cooler in the summertime. So we have a 74-degree set point. And so if we take the actual climate data for our project of what the project experienced during the monitored period, and we model the project with our same heat set points, the heat pump energy usage is within 6% of modeled usage, which is really pretty incredible for the software to be so accurate. But again, even if we had been double the space heating usage, it still would have been dwarfed by the expected space heating in a project that had a poor thermal enclosure or a code minimum thermal enclosure. And so we're really splitting hairs when we talk about the difference between an EUI of 1 or 2 versus what the baseline is. And so that's just important to keep that context. But I'd say the biggest benefit of a passive house really comes down to not so much the reduced energy consumption over the course of the year, but the load reduction and the ability to size the mechanical system really aggressively, because you can be confident in the air tightness values of the house. You can be confident that the R values and the U values are going to be what they're expected to be. And so when you're sizing the mechanical equipment, there's a huge opportunity for reducing the size of that system and not needing to add excess padding or any correction factors to account for poor quality control and construction. And to give context, the purpose we're doing this, there's the trying to make your building a Ferrari aspect of it, but there's also the how can our building impact our carbon emissions? And I just wanted to give some context on the project, because sometimes these pieces are discussed without the context of them. And basically, if the black bar here represents a building with an EUI of 30, which is actually less than what our modeled EUI for our project would have been, but I'm just going to use 30 and 15, so it can be kind of like a 50% reduction. So basically, using the Northwest Power Pool grid values for our emissions factor, we going from an EUI of 30 to 15 saves almost 40 tons in the first 10 years of operational energy. And in comparison, when you put this project in the beam estimator, it's about 30 to 40 tons of upfront emissions for the structure and the finishes and everything that you can calculate in the beam tool A1 to A3 actual. When you account for things that beam doesn't have in it, those emissions are going to be a little bit higher, but that's just to give some context. And then in comparison, which is often ignored in a lot of analysis of passive house projects, is the benefit of reducing when you have if you're using high GWP refrigerant like 410A, there's a massive impact going from a 3.5 ton heat pump in this black bar for the code house to a 1 ton heat pump. When you take the GWP warming equivalent over 20 years, it's about 20 tons. And if you take it over 100 years of that refrigerant potentially leaking out, it's about 10 tons. And in context, if you have a net zero project and you're doing site PV, you could go from a PV system that's about half the size. So that's about 4 tons of savings just on making a smaller rooftop PV. And to give context and comparison, if you added triple pane glass from double pane glass to window, that's about a 0.5 ton increase in upfront emissions for the project. And I'm not recommending doing this. I just kind of wanted to throw out a worst case scenario. If you just took your code building and then wrapped R30 XPS around it, and this is the XPS from the beam tool, which is lower than the high GWP on the XPS because the beam tool averages it out, I believe, with the newer products that are becoming more prevalent that are the low GWP. And I'm hoping that if you're a passive house consultant and you're on this presentation, you know, if you do have to use a foam product, it's important to specify the low GWP version, which would actually probably be even better than this XPS. But if we wrap the whole building in basically 6 inches of EPS, under the slab, foundation walls, roof, it add about 10 tons of emissions. And so when you compare that to the heat pump emission savings alone, that XPS could be justified. Obviously, we have better ways to insulate, but it's just to provide context. And I just have the same analysis just with a bunch of different types of insulations. If you did R30 EPS, just for context. And this project, we did double stud walls and we have about 5 tons of cellulose in the project. And so we actually have negative emissions from the storage of that cellulose. And that's, you know, what you can do. And that can be a 13-ton swing going from the XPS to the cellulose. So there's big room for using better materials to reduce the upfront emissions of the project. But in the scheme of things, it's important to keep the enclosure upgrades in context with other aspects of construction as well. And I feel like that's missed a lot. And the kind of insulation is always the boogeyman and picked on. And I'm not a huge fan of that. Another thing to consider is the timing of load reductions, which in my opinion, the timing really does matter because the winter savings, if you try to take your PV in the summer and you take all the energy that the code house had versus your passive house, and you try to do that same thing just with like short-term energy storage, like from a Tesla wall, it would take about 250 power walls to do that. And that'd be about 600,000 pounds of CO2 for those power walls to do what the building enclosure is doing with load reduction and heat pumps. So just something to keep in mind for context. Now getting into some monitored data. So during a heat wave, this was the hottest period that we had from July to August in the first summer that we lived in this home. And you can see the 1% design temp is this kind of pink line at 96 degrees Fahrenheit. And we exceeded this temperature on multiple days. And then our most critical zone, which is our upper bedroom, even on this day, which is well above our design temp at 106 degrees Fahrenheit versus 96 degree design temp, we were able to maintain 72.5 degrees in that upper critical zone. So I think that's a testament to the external shading, the zone system. We didn't have to like freeze other areas of the house to keep that upper zone warm. And then the time constant of the building enclosure as well is having an impact there. And then this is the building kind of showing the thermal mass of the building. But basically the temperature remains very stable indoor. Even when we have a day here in September where it's 90 degrees, the highest that upper zone drifted up to without any active cooling was 73 degrees Fahrenheit. And so even though this is by every measure a lightweight building, because of the external shading, because of the high performance building enclosure, limiting the infiltration, and then there's very little conductive load through the opaque building envelope, it's evident that you can maintain a really stable indoor temperature without a lot of extra mass just by reducing the input of heat, or in the wintertime by cutting the heat loss. You know, this building has 3 to 4 times less heat loss than a code enclosure. And so that's the equivalent of if you added 3 to 4 times mass in a code building, we're achieving basically our building thinks it has 3 to 4 times mass because our heat loss rate is so much smaller. And so you can get really good stable temperatures even in a lightweight passive house with a good enclosure. And then monitor performance during a cold snap. This green dotted line is the average outdoor temperature for the day, which is almost half. So the average temperature during this period on January 1st is almost half our design temperature. And the low temperature was well below design temperature. And even with that, these blue bar graphs are the wattage from the heat pump. The heat pump never went over 1500 watts, even on a day below design temperature. And the average wattage to maintain a comfortable temperature in the home was 764 watts. And this is really where I think passive houses shine on these extreme design days when the grid is going to be under the most stress, especially as we move to a winter peaking grid. Right now, the thermal loads in buildings in the summer are kind of driving a lot of like peak issues with the grid overloading. But that's as we electrify more and more heat, the heating peak load is going to be more important, and these buildings just kind of cruise along with very low wattage to basically heat with like barely the average into the heat pump, the average wattage of a hair dryer. So I just wanted to kind of give some context on that. And then another thing here is I have that outdoor temperature, and even as it approaches 0 degrees Fahrenheit outside, so the dew point air of that air coming in from outside with the ventilation system is very low, below 0 degrees Fahrenheit. Even at that, on an extreme cold day, the indoor relative humidity was stable between 42 and 45%, along with the temperature kind of fluctuated between 71 and 68. So just very stable humidity. We have the ERV core in our unit, which recovers the indoor humidity, and that's helping keep the humidity stable in the house. And this kind of just shows, like, we have some periods where in January, relative humidity, the lowest it dropped down to was 36%. And then in December, we had a 32% day. But in general, we're staying in a nice, healthy band of humidity in the 40 to 60 range. There was I had a water leak with my refrigerator. And during that period, we had a little peak over 60%, but that was kind of an anomaly. And so this kind of leads me to some monitor performance of the double stud wall assembly. There's kind of a misconception that double stud walls are riskier than a 2x6 wall. Modeling and monitor performance, at least in my climate zone and in my region, doesn't seem to indicate that. So basically, when you model a double stud wall with all the same boundary conditions, it's the only difference is you thicken the wall and keep the cavity insulation the same, all the profiles the same. You can barely see a difference in model moisture content performance of that assembly. Up here is a 20% threshold where we would consider to be a high level that's unsafe of moisture content. And this is the very inner 1/8 inch layer of sheathing on the inside face of the Huber zip that we used on the exterior wall sheeting. And so this is that moisture. See, in the first year, it's mildly elevated with the double stud wall versus the 2x6 wall because of the extra cellulose in the wall that has more built-in moisture, construction moisture, but then it pretty much has identical performance. There's some wetting to safe levels in the winter, and then they dry out aggressively in our dry climate. And I just added a double stud wall with all the same parameters, moved to Seattle just to show that even in the soggy Northwest, a double stud wall can be safe, at least in the context of a single family home with an ERV and kind of the expected humidity levels in a house like that. And interestingly, this graph kind of shows the seasonal equilibrium moisture content. And basically, the exterior sheeting of that double stud wall really kind of mirrors what you'd expect if you just had a piece of wood sitting outside. And so you can calculate kind of with the climate data of a location, what you'd expect the relative humidity to be in the equivalent equilibrium moisture content. So this is a calculation you can do for your project as well. And you can see that kind of get some context on the moisture content in the wood. And then we did the monitoring of walls as well. We did a few different types. This is the result of the all cellulose wall. And again, the only vapor control layer is the latex paint on the drywall. And the maximum moisture content of that double stud wall in the first year, which is going to have the highest level of moisture, it peaked at 13.8%. So the wall is performing really well. And you can see there's an outlet right there that could potentially indicate an air leak into that wall. But with the super tight exterior wall sheeting and using a high density cellulose insulation in that wall cavity, there was really no additional air leakage. And then in terms of just the double stud walls, just as a thought experiment, I just wanted to show our project tested at 0.012 CFM per square foot versus the 0.06 CFM per square foot of leakage that is allowed for PHIUS. And basically, if you design to a more aggressive target than even Passive House, that incremental heat demand saving is the same of going from an 18-inch wall to an 11-inch wall, or 4 inches of slab insulation to 12 inches of slab insulation. So remember, there's that. If you want to do the additional quality control and have your air barrier details dialed in, you can go beyond even the Passive House levels and reduce upfront emissions in the building assemblies by being more aggressive there. Okay, this is just the modeled versus actual CO2 in the bedroom. We put about 40 CFM or 20 CFM per person into our primary bedroom. This slide will be available to look at, but you can calculate based on the room volume and the ventilation rate, what the expected CO2 levels will be. I recommend doing that on projects if you have targets. I have an office project that is also Passive House in Boise area, and it has a Zender ventilation unit that only has the unit filter, and it has a ductless mini split that has very little filtration from the recirculating it. And so in this project, when outdoor levels of particulate spike, this project kind of follows that. It's about 20% less than outdoor. And so just doing an airtight building enclosure and not having more filtration isn't always going to be the solution. Our project, in contrast, we have not only the MERV 13 filter in the Zender unit, but we also have the additional MERV 15 secondary filter with charcoal filtration. And then our heat pump, our ducted heat pump, has a MERV 16 filter that can recirculate. And in a situation where the outdoor AQI was 157, our and PM 2.5 was at 66, we were 10 times lower in our house during the smoke event. Like, you can't smell the smoke inside the house, and you really have no idea that there's a bad air quality event, and we can keep the CO2 levels down in the house and bring in outside air without being worried about bringing in the outdoor pollutants. This is just a photo of the filtration system that we have. This is just showing the wattage of if we want to run our air handler on continuous to get more filtration and turnover of our indoor air. At 650 CFM, we'd be drawing about 65 watts. So it would be a pretty minimal energy penalty to keep the air good. I'm not going to dive into the hot water because we're tight on time, but the PV system performed about exactly as expected. This is just showing kind of the variation between consumption and demand in summer versus winter, and how there's excess PV generation in the summer where it's perfectly coincident with the cooling load. Typically, the reason for the cooling load is the sun. And so there's typically excess solar, especially when paired with short duration energy storage, where you can easily handle cooling load with low carbon solar electricity, where winter is a little bit more challenging. It gets us into long duration storage and backup sources of electricity. And so it's always important to keep that in mind, that sometimes it's worth dialing up your thermal enclosure, even if it means bumping up the cooling load during the summer and the cooling seasons. But just know that by reducing the peak loads in the winter time, you're probably going to have a much higher benefit during that process. That kind of wraps up the presentation. I think
thank you, Skylar. Thank you, Scott. Wonderful presentation. I mean, this is better than net zero, performing so well on those crazy cold and crazy hot days. Gorgeous, like, elegant details and all this data, which is so interesting. I saw a lot of questions. We are going to get to questions in just a second. Quick thank you to our sponsors.
Hi, I'd like to give a big thank you to the fine organizations that make our work at Passive House Accelerator possible. First, a big shout out to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you too to our founding sponsors, 475 High Performance Building Supply, Baxt Ingui Architects, Glavel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, Rockwell North America, Stocorp, and Zola Windows. And thank you to our champion sponsors, Icon Windows and Doors, Intelligent Membranes, Proseco, and Source 2050. And thank you to our patron sponsors, Aero Aggregates, Brennan, Brooklyn Solar Works, Euroline Windows, Coltraco Ultrasonics Micro Air Leak Detector, Inotech Windows and Doors, Lamelux, Owens Corning, RDH Building Science, Sanderson Sustainable Design, and US Engineered Wood T-Stud. Thank you, sponsors.
Wow, Bev, I'll take over with the questions. Boy, if you wanted a deep dive into some amazing Passive House details, you sure got it from Skylar and Scott today. Bravo for this presentation. And for those that are new to Passive House and we're like, what just happened? It's okay. March 1st, we go back to the Passive House 101 series where we break down the basics and get you up to the level where both Skylar and Scott are at. They are legends in it. And again, a few nominations there, Skylar, for president. Again, there's different boards and different organizations, but I think just go right to the top. We'll put you in the White House. It's I think you deserve it with this type of detail. So the list of questions is long. We got about 14 minutes until the top of the hour. And then I think in the final 15, people want to know about hot water. So we'll have to bring you back with that aspect. But getting to the queue, there are a whole bunch. We'll start off with Paul Thompson. Paul, you get to kick things off.
All right. Hello. Wow. What an amazing project. Performance and beauty. So thank you for sharing that. That was awesome. My question is, you mentioned some of the refrigerant issues with the mini splits. And I'd seen a presentation or a couple of presentations at various conferences talking about the lost carbon potential when something goes wrong with mini splits, and you lose all that energy, just goes into the atmosphere when the refrigerant boils away. Have you done any calculations, what happens, how much energy savings or operational energy is lost when you have to recharge that system? Is it a year or 2 years or 3 months? If you haven't done the calculation, there's sort of any sort of thoughts about what we can do about that, and if it's just inevitable.
I'll take that, Paul. But yeah, I developed a calculator that does allow you to assess the leakage rate and the impact, and also assumptions for refilling. That's what one big misconception is, that there's X amount of refrigerant in the unit, and that's the risk in terms of it leaking out. But it's actually greater than that, because the units are often topped off, especially in commercial situations. And so there's even a higher amount of refrigerant used than even on paper. I would say that the best thing we can do is size the mechanical system as small as possible to de-risk that. And then the second thing would be to do packaged systems where only thing you connect to it is water, and you don't have to do any on-site brazing or anything of that nature. And so a lot of the air to water heat pumps, for example, that are coming out have just that. And all you do is connect water lines to it, or glycol lines or whatever, or keeping it simple like we did on our project. Instead of having a multi-split system where there's lots of refrigerant lines running back to the central branch where it has a high propensity for leakage, the more joints that you have, and the more air handlers you have, it's not only the joints that leak, but often sometimes the air handlers themselves can leak. And so there's the fewer air handlers you have also reduces that risk. But bottom line is we need to switch to lower GWP refrigerants. And that is in progress. And the 410A is getting phased out to something that's, maybe I think half as much. And then there's refrigerant options like the Sandin has CO2 as the refrigerant. And so even if that were to leak, it'd have very little to no impact. But in terms of, I will just say upfront, heat pumps in general, you're doing more good by switching from natural gas to heat pumps, even with the refrigerant leakage issue, because of the coefficient of performance and the fact that the grid gets greener and less carbon intensive every day, basically. And so the emissions go down, whereas with the natural gas, the emissions are often undercounted and doesn't account for a lot of leakage and other upstream issues with that natural gas source. And so I would say that we definitely need to electrify heating, and most people need cooling anyway. So there's going to be an AC unit there. And so I think we need to just reduce the risk by making the equipment as small as possible and trying to seek out the low GWP refrigerant options that are going to be coming online in the next couple of years, and not doing super complex VRF systems that are more prone to leaking. So the issue is being addressed. It's just, we're kind of in that weird area for the next couple of years where we're kind of stuck with a lot of 410A on our projects.
And of course, Skylar probably has the best spreadsheets ever in Passive House. So if you ever wanted to steal a computer, go steal his, because again, steal his and the cloud, because there's some juicy spreadsheets on his computer. Thanks, Paul. Over to you, Sarah.
Hi, amazing presentation. Yes, I will also steal your computer. And the data is incredible. And I love how you're demonstrating how valuable Passive House is in the embodied carbon context and the grid context. But I wanted to ask you, so, we were doing studies of our own of the embodied carbon impact of our Passive House level of insulation. And we're finding that, we're almost meeting our targets with an R30 roof. But we're just missing them, and after multiple rounds of modeling review. And so we have to add that extra R20 to get to R50, and that in itself, that move is not paying for itself for 145 years, carbon savings from the grid. So I'm wondering, since we have a budget, right? And we're on track to spend that carbon budget in 7 years. So I feel like we need to nuance our targets just slightly to allow for a little bit more flexibility when a team can reliably demonstrate this sort of trade-off for these levers kind of things. I'm wondering what your thoughts are.
Is that a PHIUS or PHI project? Just out of curiosity.
PHIUS.
PHIUS, yeah. So I agree with you. Again, I still try to look at just how we're trained to do in Passive House. When we look at, if you just look at individual measures instead of grouping them together and taking the advantage of what the group of measures do, I really think it's really important to not necessarily look at the individual measures as much as like the end result, and especially that end result, because then you never get to that end result where then the mechanical system is, maybe 3 to 4 times smaller. And so, and then you can kind of account for that benefit as well. So I think that's kind of the first comment I'd have with you. But I think when it comes to like the roof insulation going from R30 to R50, like if you cut that heat flow through that roof in half with that measure, like it's probably not going to change the size of the mechanical system. It's not going to change the overall EUI of that system. So I'm with you there, where I agree that that's where having a good feel for EUIs helps, because I remember in my early days as a Passive House energy modeler, I would just focus on annual heat demand, which is like you're focusing on annual heat demand, which you're ignoring the fact that the heat pump, is 2 to 3 times, 4 times efficient. And so that any impact you make is actually only a quarter of that because of this site energy, because of the heat pump efficiency. And so I think having a better understanding of how it impacts the site, like the sizing of the mechanical system, and the whole kind of the holistic period aspect of it, and looking at the package as a whole, because I'm sure if you could finance that phone that has 140-year payback with better air tightness that has like a 1 month payback to help bring down the overall impact of all the measures for the enclosure combined. And so I really am careful about assessing kind of the little like individual measures, but I hear you. Like once you get it to the point where your mechanical system size isn't going to change and you just start looking at doing cost optimization, that's when I would really like a variance to like, hey, we're going slightly over the heat demand budget. The EUI doesn't change, but it has a big carbon impact. So I'm with you on that for sure. And so I think PHIUS is going to try. I'm on the technical committee with PHIUS, and these are the discussions we always have. And we oftentimes will make exceptions for projects if they make a compelling argument. So it might be worth reaching out to PHIUS on a project if it's on multiple multifamily projects, where maybe we could also look at climate data too, and you do an updated climate set with kind of the slightly warmer winters that we have now. And that might be enough to tip it to, if your climate set was updated with latest information, that might be enough to offset your roof insulation, and maybe design into a slightly stricter air tightness target. In combination with all those things, you could optimize that.
Excellent. Well, we've got a couple minutes left in the hour before we get into what we now call the final 15. Now with this earlier platform, we know that you got to get back to work. And so we'll keep Skylar and Scott for a few extra minutes so we can answer some of those questions. So if you do need to leave us, again, you got the updated event schedule. So make sure you put that into your calendar, and we will see you next week. But again, you can always hang out with the Accelerator. There's lots of stuff on the website, magazines and podcasts. And again, you can always connect with us too. You know, there's lots of things. Go meet a Passive House colleague in your neighborhood, go have coffee, talk about projects, share, collaborate, and learn, because we all need to be building better. And Skylar, wouldn't that be the day when you were working on a retrofit of the White House? I could see, maybe you don't get in there from a presidential standpoint, but at least we could get you in there to retrofit that beautiful building. And we would nominate you to take on that project for sure. So we still have a few questions.
Would it be an interior or exterior retrofit?
Hey,
interior or exterior?
It's for you to decide. Hey, I will let you figure out the model with the team and figure out what the best option is. I don't even know where to start. We're trying to figure out how to retrofit one of the Parliament buildings here in Canada. So we get those issues. So
interior is a staff replacement.
I think we could segue pretty quickly. So coming back to the questions for today's presentations, I mean, maybe that's a future show, is how Skylar would retrofit the White House. That's maybe one of our bonus Wednesdays of the month. Okay, Sandra, we will hit you up in a second. Again, if you do need to leave us, we appreciate you showing up. Enjoy the rest of your day. Thanks for joining us. And again, you got some great juicy nuggets from both of these presenters today. So enjoy. Let's carry on. Sandra, if you're still with us, I know you were next in the queue. Graham left, so he gets bumped and you get brought up.
Graham and I were wondering about the wall assembly, and you got some great hygrothermal performance data from the wall. And I'm just wondering if that level of performance was predicted, if you were worried about it, especially with the cathedral ceiling and possibly the north side that wouldn't get as much solar radiation and drying out during the summer.
Yeah, so the double stud wall assembly is on the north side that was monitored. So that's kind of the worst case scenario, and it's very shaded there. On the roof, we had a very, like our house couldn't have been a 1/4 inch taller because of the historical guidelines in the neighborhood. So there is a 2-inch layer of HFO closed cell foam on the roof deck, and then dense packed cellulose after that. And so that is monitored as well. We also did a couple of test roof assemblies, and the moisture content is much lower, but we also have a dark roof. And I don't know if you've done much modeling of light roofs versus dark roofs. If we had a light roof, that moisture content of that unvented roof assembly could be considerably higher regardless of the approach, because there's so much less radiation. Even though there's not a ton of radiation on that north side, it still gets more with that dark colored roof. So when it comes to roof systems unvented, that is a little more dicey because it's a completely different hygrothermal dynamic with the night sky radiation that cools the roof at night. And so I would tread carefully doing anything kind of beyond kind of prescriptive code for that. There's ways you can do it with interior membranes. Again, when you have a steep roof as well and it's thick cellulose, you get into some quality control issues with getting that cellulose packed tight enough not to settle at the ridge long term. So all can be overcome with good quality control, but I would be want to be very involved on a project that had it. And then in terms of the wall performance, it's performing better than the hygrothermal model, and our humidity conditions are actually higher than the WUFI assumed humidity conditions. And so it's performing as well as expected based on people in my region have been building double stud walls for decades. And so basically if a 2x6 wall will work, in your climate, and I would verify it climate specific, but at least in my Northwest region, a 2x6 wall and a double stud wall effectively perform identical. This idea that there's enough heat transfer through R20 cavity insulation versus R40 cavity insulation to kiln dry the exterior sheeting, that's just kind of a false argument, because there's so little heat through the center of cavity through that R20, it's not enough to necessarily dry that wall out. That kind of goes back more to like when you're looking at historical buildings of going from an uninsulated wall to an insulated wall. But when you're going from like a really well insulated wall to an even better insulated wall, the hygrothermal dynamics don't change that much. And so if a 2x6 wall would be appropriate for your project without exterior continuous sheeting or a vented, like a lower perm exterior sheeting, then a double stud wall will typically work. Yeah.
Sandra, again, good point about the Canadians burning down the White House. Yes, we've done a few of those things in our history.
Back in the 1800s.
Yeah, it's just how things worked. Skylar, maybe I'll interject quickly just because I again appreciate the double stud comparison for again Boise versus Seattle. And I've kind of, when talking to clients that are into passives, I kind of draw the line of like the Rockies are kind of like the divide between the double stud versus the 2x4, 2x6 with insulation. And only because you can get into the cost and you get into diminishing returns of insulation. But when you start a project, do you normally start with a double stud wall on all projects? Or do you like, what's your kind of rule of thumb? Mine's always like the Rockies is the divide, but what's your kind of thought?
For me, kind of what is the most important is what the builder of the project is going to be comfortable with, and then we'll make it work hygrothermally. And if it's a multifamily project, you're going to have a way in the Northwest, you're going to have a way different, like a multifamily project in Seattle, like, if 2x6 walls can kind of turn into oatmeal on those projects if you have high humidity and high occupancy in a multifamily project, because you have really high outdoor dew points. So it really doesn't dilute the indoor air that much in the wintertime. So everything should be a case by case basis. I would say for most single family construction, you can get away with a double stud wall just because the buildings are generally fairly low occupancy. If you have elevated humidity in the house, like you have a steam humidifier and have to keep your humidities elevated, then you're going to have to move to an exterior insulation approach or like a pass-through approach without exterior wall sheething. So it's really, again, project specific. But I found that there's just so many making the double stud work in kind of the high-end single family residential market. It really works well because we can avoid doing all the external foam on the wall foundation, and we don't have to protect all of that foam. We don't have that big ledge as we transition. So we get rid of a lot of thermal bridges with less foam use on the outside that needs protected. And it makes a lot of the detailing and inspection a lot easier. And then if you add a penetration, the sheeting's right there, it's easy to inspect. And you can really just focus on making one layer of the building super airtight, super watertight, and focus on the quality control there, and it's visible and easy to see as the rain screen strapping goes up. This wall does have a rain screen as well, and so that changes the whole dynamic as well too. And so it's just a lot of variables. It's hard for me to give rules of thumb, but I would say in most single family applications, a double stud wall will work. And if I'm in a market that the builder is comfortable with doing exterior mineral wool or Gutex or whatever, then we can go that route all the time. But I've done tons of projects, my own personal projects with Larson trusses on the outside full of cellulose and the exterior membrane. And in retrofit projects where that made more sense to do it from the outside. But I would say the double stud wall is just the easiest to design for and plan for, and it helps mitigate a lot of thermal bridging. You don't need to do any foam under the footings anymore, which is a huge benefit as well under the exterior perimeter footings, still on the interior footings. And so there's just a lot of benefit to doing that.
Great stuff. Okay, great. Thanks. Getting back to the questions, Mark Karsten had a question. Mark, are you still with us?
Yes, I am. Thanks. Great presentation. I was confused. You had a Zender system, and then you also had what appeared to be a separate the heat pump connected system that had the 3 zones. And so it looked like you had 2 parallel ducting systems. So that's kind of question 1, clarify that. And 2, on your wall assembly, do you have a utility chase? I'm here in Minnesota, so very cold and very wet summers. And so the idea of having utility chase, and that's a permanent barrier that's never violated, is really important. Does your double stud, where is there an interior? Do you have a utility chase in that, or how do you separate?
Well, we'll start with the first question. So on all the passive, pretty much on all the passive house projects I work with, we always run an independent duct system for the Zender unit or for the ERV unit, because otherwise it's almost impossible to commission the system and balance the system. And so we have separate ductwork for the fresh air supply from the ERV or the HRV and exhaust, and that replaces all the bath fan exhaust in the house. And then we have the heating and cooling system is independent of that, and they don't communicate with each other. They're fully independent. And so our Zender unit is fully ducted, so we can commission all the flows to each room to ensure it's getting the ventilation that we want. On projects that aren't passive house, that are kind of lower budget projects, you can tie the ventilation system into the ductwork of the heating and cooling system. It just gives you less control. It's harder to balance and commission the system. And so that's typically why we don't do that on our passive house projects. In terms of the wall assembly, I've done double stud wall before, where we have like an interior plywood, and then we do a non-structural chase on the inside. So that way the wall really has the interior and exterior air barrier. I would say when you're in a situation where you use high density cellulose, which is quite air impermeable, and you have very stringent air testing on site, like our wall assemblies are like basically zero air leakage. And if there's no air leak going out through, like there's not going to be, even if you have a hole in the interior drywall, air is not going to flow to the outside because there's no air leak through the wall, and there's no way it's going to go through that high density cellulose insulation all the way to the sheathing, unless the house is pressurized mechanically. But we have a balanced ventilation system in this house. And so if you want to be super conservative and you're nervous about doing a double stud wall, then your solution is to do the mechanical chase with an interior vapor control and air control membrane that you detail for air tightness. But my preference would be to take that money that we're spending on that interior vapor control layer and that interior surface chase and spend it on making my actual water control layer, which is really what's going to cause a wall assembly to fail. It's going to be a water induced event. And so putting that money into doing fluid applied air barrier or fully adhered air barrier system, that's also the water control layer. So spending that money on a better water control layer system and a rain screen system would be money better spent to me. But if you can afford that and the interior layer, you can add the interior layer too. But I would model the project for the client and see if it's necessary. And I'd also do an analysis in Woofy where you can simulate an air leak into that wall assembly to see how big of an impact it's going to have, to see the kind of the risk level the client's willing to take.
Okay, great. 2 quick follow-ups. So you're not worried about that leak at the electrical outlet because your outside wall barrier is let's just say perfect, or it's really, really good. It's high quality. And the second question is you think you get that with a zip system and wet flashing on all the joints, wet sealing on all the joints?
Yeah, basically before the dampers and everything went into the house, I mean, the whole house had like 20 to 30 CFM of air leakage. And so like pretty much all of the air leakage that's happening in this building is happening through the intentional mechanical openings and the dampers for the makeup air system, and then the windows and doors. And so there's virtually no air leakage through the wall or roof assembly. And when we pressurize with theatrical fog, there's no fog that comes out anywhere other than at window joints and the mechanical penetrations. And so I'm confident that the wall is airtight. And then the distinction to make is if you're using a low density air permeable fiberglass bat that is even prone to sometimes, especially if there's gaps in the installation, there's convection that can go from the outside to the inside naturally. That's a whole different ball game than a high density packed in conformed cellulose material, or even a high density blown in fiberglass. And so those just have way different air permeability properties than a low density fiberglass bat that's like 1/2 pound density instead of something that's like, 3 to 4 pound density. It's just totally different dynamic. And then there's also the moisture buffering that you get from the cellulose that helps the assembly as well. But even with the high density fiberglass, the system is still hygrothermally sound and is not going to be prone to kind of those convective loops that could transport indoor moisture to the outside of the wall without that interior air barrier.
Okay, great. Thank you. Appreciate it.
Of course.
Great stuff, Mark. Got 3 minutes left now. Michael Ingwe, are you still with us? I think he's somewhere hot and sunny. So his question was the charcoal filter the Zender product or third party? I think the answer is third party, but
no, that's a Zender product. So it's the Zender Comfo Well system. I basically am advocating to put that on all my projects in the West that experience these severe smoke events. Specify the Zender Comfo Well. And one thing I've noticed too is when you look at their product data for that unit, for that air filter housing that connects to their tubing, use the biggest air housing that gives you the biggest filters, and there's almost no additional wattage. That was something that I was concerned about, was that the Zender was going to have to use a whole bunch of extra fan energy to push through those filters. But because we have a 350 unit, but we have the larger manifold that's used for like the 600 unit, the filter surface area is bigger, and there's like just the unit really uses like 3 to 4 more watts on our normal operating speed, and maybe it was like 8 or 10 more watts on like max speed. But obviously, when there's a really bad smoke event, and we put those filters in seasonally, which is something I should have mentioned. We only put those in during a smoke event because they're quite expensive filters, and we don't want to be having to replace those out every 6 months or something. And plus, there is a little bit of extra fan energy too to have them in, and you can hear the fans working a little harder, so there's a little more unit noise. So we definitely, when it's on boost especially, so we definitely only use those seasonally when there's bad outdoor air quality.
Gotcha.
But there's Zender systems. Yeah, there's Zender provided.
Great. No, that's great. I know early on, Albert at Small Planet had a bit of a hack, so I'm glad that Zender provides the whole package now. That's great. We have Ian and Chris. Whoever gets to the mic first gets the last questions. And I know Chris had a few, so.
Hi, it's Ian. Just back on the Zender unit, there's the Comfafon, that's the ground loop. Have you ever used that and modeled that?
Yeah, I have that in my actual office. It's just up the street from here that Scott also designed, and I have it. I would say it definitely pre-cools the ventilation air in the summer, but and then in the winter time, it obviously reduces the defrost usage, electricity usage. But for my projects, I'm really not recommending it anymore. For PHI projects, I'd be more inclined to, because the heat demand doesn't scale with the how cold the project is. So you could add one of those comfort funds and reduce your insulation requirements considerably, because it actually helps you on heat demand. It's kind of considered a passive measure because it improves the recovery efficiency of your ERV or HRV unit. And so, but I've noticed that it's not like, if a day was going to need cooling, having that comfort fan doesn't, like, even though that ventilation air is minimal, like the cooling, it's like not enough to like not need actual active cooling, because there's just so little airflow overall from the ventilation unit. And so it's not really like passively heating or cooling the house. It's just kind of like shaving like the annual energy consumption a little bit, in my opinion. Yes. And then I'm a little less enthusiastic about it because I had a leak from the system that is user error, because I never installed one before. And so that kind of gives me concern too, is if issues I've had with other ground source heat pump systems and too, where it's like you install the system and the water kind of just leaks a tiny bit each year and has to get refilled. It's kind of not an ideal situation because it's hard to like get at and fix. But if I had done a loop more like a bonded ground source heat pump instead of using mechanical clamps, I'm sure it wouldn't have leaked. And so that kind of, having to sort that out was kind of a pain. It's just one more moving part, I guess, and one more filter to change.
Gotcha.
Yeah, thanks. Yeah, that's what I kind of got from when I was doing the modeling on it, that it kind of shaved those temperatures, but you still needed extra heat or you still needed extra cooling.
Well, okay, Skylar, Hans texted me. He just wanted to know what was the model of the moisture sensors that you're using?
OmniSense, you basically have a gateway that connects to their cloud. And so all the data goes from the sensors that get screwed into the wall. And I think the battery life, based on it's really important. I've done projects before where I did their default interval data and it's like very frequent. And then the batteries only lasted like 1 to 2 years. But if you do like a hourly logging period or a daily logging period, you're going to get years of battery life out of them. So it's a pretty remarkable sensor, and they just like screw into the face of the sheeting, and that's OmniSense. It's easy to buy online. I highly recommend it. It's given me more confidence in kind of my hygrothermal modeling because I can go back and look at how actual projects are performing and compare that to the hygrothermal modeling.
So Hans is having trouble with his computer overheating. So it was Omni or OmniSense?
OMNI.
Thanks.
I think I had the logo in the slide. It's OmniSense.
I think you did too. Well, Skylar and Scott, we could take a deep dive into a whole bunch of things. Again, when we deal with the construction tech, where we deal with the technical, the techniques, and the technology, I think we could either just talk about OmniSense or the recirc line, because I mean, that was some good nuggets right there. So Scott, we haven't heard from you in the last little bit. Any parting words that you want to say from this project, or anything from a learning standpoint that you're just like, not just, hey, I love working with Skylar, because I think we all would love working with Skylar, but anything that you want to say as we wrap up today?
I think I would just echo the same kind of conclusion on the double stud walls about the constructability. I think that the first passive house project that I worked on, we did an exterior sort of Larson truss. We did that again on Skylar on a different project with him. And it causes a lot of construction. I mean, there's just a lot of different details you have to deal with the exterior systems that I think are greatly simplified with the double stud wall. So just from strictly how to communicate these details to a contractor who might not have done a passive house before, there's some huge advantages in just getting a passive house actually done. The exterior stuff can be complicated. So I would say, obviously, depends on the climate. You got to really think about the go through the analysis, WUFI, all that stuff. But if you have the chance and it seems like it's working, I think you can have a simpler solution. The other thing I'd say on this particular project that I think I learned a lot about was that air zone system. So what basically the controls. I know Skylar spent a lot of time sort of working through the control systems for that. And so, but I think that's a kind of really interesting solution that's out there for these types of projects where you don't need, it's tricky to have, I need 3 zones, but I don't want to have 3 different, air handlers or mini split heads. So this was a good solution. And yeah, I think that's about it. Skylar, did you want to talk any more about the hot water system? I know people were asking about that. I don't know if there's any time
so basically
left.
It's inconclusive. I worked with Sandon to try to resolve the issue, and I'm adding basically flow sensors to the unit so I can actually get a better idea of if it's a water usage issue or if it's a COP issue. The problem is even when the recirculation pump is off and I have verified all the check valves, we're getting a pretty decent demand, even when we're out of town and there's no one at the house. And so where the unit's running and cycling quite a bit when there's really no hot water demand. So it could be one theory that was proposed is if you use too little hot water, the tank can you kind of don't have enough cold inlet water coming in. And so we're working through that. I'm going to have an answer this time next year and kind of have a better feel. But I have other projects with Sandon units that are using half as much electricity. And so I don't know if it's my problem or a unit problem. So I'm not pointing fingers at Sandon at this point, but it's still performing way better than a direct hot water tank would have. And it's performing probably comparable to where a packaged heat pump hot water would. And so even though it's like a lot more than the model data, that's like it's like when you double or triple a very small number, it has very a very small impact on the overall performance of the building. And so just, it's all about context, I think. Like, I'm not dissatisfied with how the unit's performing. I'm just trying to figure out what's going on.
Great stuff. Okay, well, we got to wrap things up. We're already over time. Again, Scott and Skylar, what a great presentation. Again, like I said many times, some real juicy nuggets there. It's great stuff. So hopefully everyone, we'll see you next week. Continue to learn, share, collaborate in the efforts of building better. And Zach and Kim, I'll let you guys hit the exit button.